So this is the famous Gibbs distribution. So let me state the first result. Number one, the Gibbs and the second one is what you told me, beta tends to infinity implies on this set of okay, so far so good. Now, how Cerny was doing that, before we try to solve this problem, let me try to consider some other related problems for which people had easier solutions. Let's say I have a function of several variables. Let's say x1, xp. So there are p variables, and I have a function of those p variables, and let's say each xi takes values in some finite set A. Now, this function f may not have a nice formula, unfortunately. Okay, for example, in the traveling salesman problem, these x1, x2, xp may represent a permutation of the sites that represents a path, and then given any path, you may be able to calculate what is the total distance traveled, but you don't have a nice formula for f, right? For such a function, let's say to make things simple, which is not true in the case of traveling salesman problem. For example, if you have used the site 1 at the first place, then you are not going to use the site again, because the salesman is not going to travel to the same site twice. That's the standard constraint. Okay? But let's say all these variables xi's are freely varying on some set A, and this is again, I assume, a real valued function which is positive. See, this condition that this is positive when we are dealing with finitely many possible values for the x's is not a big condition, right? I can always add if f is taking some negative values, I can always add a big constant to the function f and redefine my function so that it is positive. Okay? So we will always consider the function f to be a positive function. Is there any simple method for minimizing this function that you know? For example, what happens, say if I try to minimize coordinate wise, what will happen? Let's say I fix all the variables from x2 to xp and minimize over x1. So let's say first I vary x1 and find the minimum value. Then whatever the minimum is, I fix it there, and then I vary the second one, and I do like this, and then I come here, and then I may again come back here. Okay? And I go on doing this for some time. If I do that, is there a guarantee that I will get the minimum? You have any example to demonstrate that? Why do you think that that is not the case, that you will have the minimum? Or anybody knows any special type of function where it will work? Is there any special form of the function where you can prove that this technique of minimizing one variable at a time will give you the global minimum? Yes? You are saying something. I didn't hear it clearly, but can you say it louder? So you have any guess for what kind of function this technique will work? See, if this works, that is very simple, right? And then the minimization problem is much simpler than the original minimization problem. If you can solve the minimization problem by taking one variable at a time. Yes, what did you say? For convex function, will it work? There's no reason that for convex function it will work. Something much simpler than that you can think of. So additive functions or something like the when f. So it's like when your function f has this form that fx1. So it is like say f1 x1, f2 x2. For such functions, it will work, or if you have product and such things, okay? So there are some special types of functions for which it will work. Not that it will not all work always, okay? It will work sometimes. But also it is true that it will not work always. Can you think of a simple example where it will not work? I have a baby example here. Let's say this A is this set 0, 1, P equal to 2, and my function is defined like this. F01 is equal to 5, F11 is 2, F10 is 3, F00 is 1. So let's say I start from here. If I minimize over the first coordinate, I'll come here. And then if I minimize over the second coordinate, I will not go there, I will remain there, but I will never hit this one. So it will not work. Now what really goes wrong with this example? See what is happening here, do you see that if you start from there and minimize across first variable, you come here, right? Because you are fixing the second variable, you change the first variable from 0 to 1, you get this, and if you keep it 0, it is 5. So between 5 and 2, it's definitely this is preferable. You are minimizing, okay? So this is preferable. Now if you try to change the second variable, if you change 1 to 0, you will come here and that will make it 3, so you will not go there. So you are trapped there, you are never coming there, okay? What is exactly the problem with this example? This is a very small and simple example, but it teaches you a lot of things. What is it that it is telling you? Depends on starting value, and if you do it like this, you might get trapped in something like a local minimum. You are not getting the global minimum, okay? So in some sense, when you are minimizing it across the coordinate, it's a sort of like what they call it, like a greedy algorithm, okay? It's a greedy algorithm, so you might get trapped in a local minimum, and then you never come out of it, okay? So the one alternative is that, okay, then if it is like this, I can always randomly choose points, and then of course, if I randomly choose points, at one point I will get kicked out of that local minimum. So if I take my random start, then this random start will sometimes get me out of this local minimum, and so then I will hit this one, okay? So in some sense, this Gibbs distribution tries to build on these two things, okay? So the idea is that you should minimize, but not in a greedy manner, and there should be a way to get out of local minima if you get trapped there. And that's exactly what we will see now, how it is done.